Today we're going to uncover the incredible chemical journey of metal. It's a really amazing story of transformation. How we take a rock that looks pretty worthless and turn it into the very stuff that builds our entire world.
Just think about the aluminum foil in your kitchen for a second. What you're holding is the final product of this long, fiery, incredible journey. In this explainer, we're going to dig into the science of metallurgy, which is basically the art of turning raw ore, like this rock right here, into the metals that kind of define our lives.
So where does a journey like this even begin? Well, when ore gets pulled out of the earth, it's not pure metal, not even close. It's mixed with a ton of other, junk. So the very first step is a really important one, separating the good stuff from all that worthless material.
Now, this unwanted material, it's actually got a technical name, gangue. Just imagine you're panning for gold, right? The gangue is all the sand and gravel and dirt you have to wash away just to find those little shiny flakes. So before we can even think about making metal, we got to get rid of all this gangue.
And to get rid of it, metallurgists use some seriously clever physics. For heavy ores, like iron ore, they might use gravity separation, which is basically a fancy way of just washing away the lighter waste. For other ores, like lead ore, they use a process called froth flotation. In that one, the ore particles literally cling to oily bubbles and float to the top. It's pretty ingenious. And for magnetic ores, the solution is even more direct.
So this is magnetic separation, and it's just such a beautifully simple idea. You have the crushed ore on a conveyor belt. It goes over a magnetic roller, and the magnetic ore particles, they just cling to the belt for a split second longer. And that's all it takes. They fall into a separate pile from the non-magnetic gangue. It's a really elegant way to sort the valuable stuff from the worthless stuff.
Okay, so now that we've got our concentrated ore, the real chemical transformation can finally begin. We are heading into the trial by fire. This is where things get hot, and I mean really hot, to fundamentally change the ore's chemical makeup and get it ready for the final extraction.
There are two key methods here, roasting and calcination. But they both have the same critical goal, to convert the ore into a metal oxide. See, roasting heats the ore with plenty of air, using oxygen to transform it. Calcination, on the other hand, heats it without air to drive off other things like carbon dioxide. So why do all this? Well, it's because metal oxides are just much, much easier to break down in the next stage.
And that brings us to smelting, the iconic fiery furnace stage everyone pictures. Here, that metal oxide is heated to insane temperatures with what's called a reducing agent, which is often carbon. You can kind of think of the carbon as a thief that comes in and just steals the oxygen away from the metal. And what's left behind? Our crude, molten metal. Any leftover impurities form a layer of waste on top called slag, which you can just skim right off.
But get this. Here's a fascinating little twist called auto-reduction. In some cases, you don't even need to add a reducing agent like carbon. When you're extracting copper, for example, the copper oxide and copper sulfide that were made in the last step, they actually react with each other. They basically do the job themselves, and poof, you get pure liquid copper. It's a fantastic little bit of chemical efficiency.
Now, the metal that comes out of the smelter, like that blister copper we just mentioned, it's not quite ready for prime time. It still has tiny impurities in it that can mess with its strength and other properties. So, to make it truly useful, it needs one final polish. We call it refining.
And the techniques for this final stage are incredibly sophisticated. You have things like the Mons process, which uses gas to carry away pure nickel, leaving junk behind, or the Van Arkel method, which does something similar for metals like titanium. But one of the most common methods is electrolytic refining. This uses an electric current to dissolve the impure metal and then redeposit it, literally atom by atom, as an ultra-pure layer. We're talking purities over 99.9%. It's just amazing.
And just like that, we've come full circle, from that humble piece of bauxite rock all the way to the aluminum foil in our kitchen. The very properties that make that foil so useful, how light it is, its strength, the fact that it doesn't corrode, it's all thanks to this incredible hidden journey of refining. Every single useful property is unlocked by this process.
Now, this whole complex process, it might seem like a totally modern invention, but the art of metallurgy, it is ancient. And to see just how sophisticated our ancestors were, we have to look at a true marvel that kind of defies everything we think we know about the past, the Iron Pillar of Delhi.
For more than 1,600 years, this iron pillar has been standing out in the open, completely exposed to the rain, the humidity, and all the pollution of Delhi.
Exactly. We all know what happens to iron when you leave it outside, right? It rusts, it flakes, and eventually it just turns to dust. So by all rights, a 1,600-year-old iron column should be nothing more than a reddish-brown stain on the ground. The big deal is, it's still standing. It's this silent testament to some kind of forgotten knowledge.
For 16 centuries, it's weathered monsoons, brutal heat, pollution, and yet it shows almost no signs of serious rust. It is still there today, this monumental puzzle for scientists and historians, challenging everything we think we know about ancient technology. I mean, how on earth did they do it?
Well, the answer seems to be in a sort of happy accident of ancient chemistry. Modern analysis has found this super thin protective layer of a compound called misoite all over the pillar's surface. This layer, which is a unique form of iron oxyhydroxide, formed naturally because of the high phosphorus content in the iron they used. This microscopic shield is incredibly stable, and it's acted like a perfect barrier against rust for millennia. It's a testament to the incredible skill of ancient metallurgists, whether they did it by design or just through masterful practice.
You know, the key takeaway here is that our world, both the ancient one and the modern one, is built on these incredible hidden transformations. From the aluminum foil in your kitchen to an ancient pillar that defies time, every single piece of metal has a story of fire and chemistry and human ingenuity. So the next time you hold a key or a fork, just remember the extraordinary journey it took from being a simple rock in the ground to the object in the palm of your hand.